working here at CITA after getting his PhD in Caltech for 2 years, and then he moved to the Maxim University as a CITA National Fellow for 4 years. After that, he went to UBC, and since 2006, he's working as a professor at the University of the Pulsar University. And he has been working mainly in plasma and high energy astrophysics, and today he's going to talk about gamma ray emission from Pulsar.
Thank you. So, very glad to be back at CITA. I know some of the people in the audience now more than 20 years. That's a lot. So, yeah. But I would like to start this presentation with a little bit of a kind of historical philosophical discussion. So I'm just freshly back from a half-a-year sabbatical in Florence, and that was the view from my office window in Cherenkov. And behind this building, there is a small villa where Galilei was basically imprisoned for the last 10 years of his life after he was judged by the church. And that this kind of walking through this through his house reminded me that some time ago I read his memoirs, and that was very interesting, and they had some interesting implication for our lives. So Galileo was born in Pisa, and Pisa at that time belonged to the Kingdom of Florence. But most of his work he did in Padua, and Padua belonged to the Republic of Venice. But he always wanted to go back to Florence, from the Republic to Kingdom. And here what he wrote to Cosimo Medici, the prince there. It is impossible to obtain wages from Republic without having duties attached. So long as I am capable of lecturing and serving, no one in the Republic can exempt me from duty while I receive pay. I can hope to enjoy these benefits only from an absolute ruler. So in modern language, he didn't want to teach, and he didn't want to write grant applications. He wanted to be fully dependent on an absolute ruler who would give him scientific freedom. And he did move to Florence, and the rulers quickly died, and very soon Galilei was given to the Inquisition, which would have never happened if, some people think, it would have never happened if he stayed in the Republic. So, this story I think tells us that it's much better to have duties attached to our freedom than be dependent on an absolute ruler. Okay, good. So now to the main topic of this talk is pulsars. So pulsars is one of the main targets of the Fermi satellite. Fermi has been exceptionally productive. It has detected more than 100 pulsars, about 100 MeVs, Vela, Geminga, Crab. And they all have kind of similar profiles, double-peaked, like this. So Geminga, Vela, and Crab are the three brightest gamma ray pulsars, and I will discuss a lot these three particular pulsars. And since they're the brightest, one would expect that analysis of these brightest pulsars has some implication for the general population of pulsars as a whole. Okay? So, the models of pulsar gamma ray emission. Until the Fermi, there were two competing models, which were polar caps and outer caps. So, this is a neutron star, this is closed field lines, imaginary light cylinder, and there are some open field lines that cross the light cylinder and closed field lines. So, the two models until recently were polar caps, meaning that emission is produced somewhere close to the neutron star. And that basically, that's strongly excluded now. Spectra are not right, it doesn't fit profile, but they had a well-defined physics. And the dominant model now is that gamma rays are produced in the so-called outer gaps, close to the last closed field line, somewhere in the outer sphere, somewhere close to the light cylinder. The problem is that the physics becomes very messy if you're far out, because very different things can influence you. But the models that, this was first suggested by Chen and Ruderman in '86. But these outer gaps models produce a very good geometrical fits. Meaning, if you assume some kind of a structure of the magnetosphere, and it doesn't really matter the details of it. Some people take dipole, vacuum dipoles, some take rotating dipoles, some take frost-free. All these models they're more or less equally well can accommodate the profiles. And what people basically do, they say, oh, let the emission be generated somewhere on these field lines. They paint these field lines, emission is generated right along the local field line, and they get these very nice fits for the profiles. But this doesn't say what is the emission mechanism. What is it that produces a photon along a given field line?
So I thought Stokowski could get quite nice bits of the curve sheet of the separatrix.
Yeah.
Which is different than the...
It is somewhat different, but it is highly closely related to this. Yeah. So, until recently, and in many people's minds still, the dominant emission mechanism was the curvature emission. And the idea is that if a particle is moving along a curved field line, it emits a photon, which depends on the Lorentz factor of the particle and the radius of curvature. So this has been the dominant emission mechanism. And generally, the problem is very difficult. It's hard to solve the full electrodynamic picture, because the electric field that accelerates particle along the field also can lead to pair production. Well, the pair production of these accelerated particles. The produced pairs short the electric field. This is all non-local, meaning a photon produced at one point can pair produce. It's a very complicated general picture, which is still unresolved. But typically we have electric fields which is a small fraction of the magnetic field, of the order of %. Also, these models need a very, very high Lorentz factors, almost up to the radiation reaction limit, up to the maximum of 10 to the 7. On the other hand, when people try to do the details of pair production, they don't get Lorentz factor larger than about 10 to the 3 or 4. Still, this model has a clear prediction. Above the spectral break, meaning above this radiation reaction limit, the spectrum must be exponentially suppressed. This is how the synchrotron or curvature emission works. So I got interested in these models quite late. And so the first bell came from the so-called imaging atmospheric Cherenkov telescope. And what they observed is if a gamma ray, a high-energy gamma ray above about 100 MeV, if it comes, it hits the atmosphere, it generates a shower. And then by observation of this Cherenkov light from the secondary shower, you can infer the energy in the direction of this gamma ray. So the first thing that really got me interested is in 2008, the MAGIC telescope detected crab at 25 GeV. I thought that is a bit too much. But it turned out that it's not high enough by a factor of a few. And I will explain what do I mean by that. So the real breakthrough came with VERITAS, and I'm part of the VERITAS collaboration. It has 4 telescopes in Arizona. So from 100 GeV to several TeVs. And VERITAS detected Crab above 100 GeVs. And that is really important. And what you can see is the cutoff is non-exponential. So the green points is the Fermi data. They end up at about 30 GeV. And this was the fit with the Fermi data with an exponential cutoff. Here is one magic point, and here are VERITAS points. And the cutoff is clearly non-exponential. This runs contrary to the prediction of the curvature emission models. Another important point to keep in mind is the interpulse is brighter than the main pulse. So just keep it in mind. So why magic was not high enough, but VERITAS is sufficiently? Yes.
Can you just go back and give the definition of the interpulse and the main pulse?
Later, I will give a comparison. So this is in radio and in X-rays. This is the main pulse, and it is much brighter than the interpulse. But later, I will give a very nice picture comparing a different wavelength. Yes.
Maybe you're about to say this, but can you say why the curvature emission would be expected to show an exponential curve?
Just like with synchrotron. If you have a charged particle moving on a circle, the emission is exponentially suppressed at frequencies which is gamma squared times the rotational frequency. Right? Gamma cubian. So, curvature emission near the light cylinder is excluded. And the idea is the following. Astrophysical electric fields are typically less than a magnetic field. So then when equate acceleration by electric field, which is a fraction of the magnetic field, or a fraction of the inductive electric field, to the curvature losses in radius of curvature, which is fraction or can be parameterized with the light cylinder radius. And then you see that if you crank up accelerating electric field to be equal to the magnetic field, which is the absolute maximum, you still cannot go beyond 150 GeV. All the models, all the radiative models, they predict the accelerating electric field or % or so. And that's why magic was not high enough. Magic was a few times smaller than this, so you can still say, oh, maybe electric fields in the models are underestimated. With VERITAS, it's clear. Curvature emission cannot accelerate particles to high enough energies. Curvature emission cannot produce particles with photons with high enough energy. So, detection of Crab above 100 GeV with non-exponential cutoff excludes curvature emission in Crab. Then we can do the same thing with other pulses. In Fermi range, they also show a break, and then one can calculate the ratio of this break to the maximal break that you expect for a given speed period and magnetic field. And you can see that this rate goes above unity. So this is another hint that the breaks are not the curvature breaks in the whole population. So, the implication of Crab detection by VERITAS. Spectral break in Crab is not due to the curvature emission of the maximal energy particles. And that has been really strange, the paper has been rejected 2 times. The first referee said, the claims are so strong that they need to be better substantiated. The second saying, but nobody believes in curvature in Crab anyway. So it was really well. Alternative possibility, inverse Compton scattering, and the breaks would be due to detail of the particle distribution scattering cross-section. And of course, one of the main arguments, this was about a year and a half ago, was, but Crab is so different. What about other pulsars? Okay, as I mentioned, there are 2 other bright pulsars, VIL and Geminga. So here is Fermi spectrum of Geminga. And it was really strange for me. You know, I'm a theorist. And here is a plot created by a collaboration of 100 people whose bread and butter is data analysis. And I'm a theorist. For me, data analysis is like a holy cow. You don't touch it. Because it's a, but if you look at these feats, they're not very good. But then my wife is the graphic designer, and I can draw a straight line in a Photoshop. And look, this straight line in a Photoshop goes not only through the error bars, but through the data points even. This is obviously double power law. Okay? So, well, I cannot publish a data feed with a PowerPoint or with a Photoshop, so I need to do data analysis. But the last time I did data analysis was some 20 years ago in some first year laboratory physics with logarithmic paper. But happily the software is good enough now, very theorist friendly. So here is this highest energy points for Geminga. Here is straight feed, which is the power law. And here is the exponential, and the chi-squares are just different. And by the way, this is a logarithmic scale, and these error bars are actually the smallest. And it's because at these high energies, there is no background. So every photon is is the source. So these error bars are actually physically much smaller than these ones. So this is kind of a data analysis, theorist data analysis that's showing that it is a power law. So why didn't Fermi notice this? Here is an explanation. If you do a broadband feed, the way people do this feeds, they take all the data, they take a model, and they calculate chi-square, roughly speaking. So here is the data. They take some model, and the model one is exponential and another is double power law. They calculate the chi-square. The exponential was a bit better, so they concluded that exponential is a good fit. But if we look at the errors for the double power law fit, we see that they're not random. Which means that most of the errors for the double power law fit are accumulated in the middle due to the arbitrary parameterization of how one power law rolls into the other power law. Does it make sense? Because let's take some simple analytical form. So we take something there. Well, but all the errors come from here, from arbitrary parameterization. And if we play with somewhat different parameterization, we can reduce this chi-squared. And for example, with Vila, and also with Geminga, playing with different parameterization of the role of I can reduce chi-squared. And I think this is an important data analysis point, physics. And physically, it's not only data analysis, because then the implications will be important. If it's a power law, it is likely to be inverse Compton. If it's exponential, it's likely to be curvature. With Vila, it's a bit uncertain. I can get chi-squared for the double power law as good as the exponential. But again, I am trying different parameterizations, and probably there is one that will really drop down my chi-squared, but I don't know it, because I'm thinking in terms of simple functions. Yes?
Does inverse Compton always give you a continuous power from the low energy?
Well, we'll get that. We'll get to this. So, out of the three brightest gamma ray pulses, two are inconsistent with exponential cutoff, and the third is consistent with double power law. Okay? That's a strong, another strong indication that it's not curvature. So, spectrum and profile. So here is a spectrum of the Crab pulsar, and there are two bumps. One is a broad UV X-ray bump, and there is a GV bump. And here are the profiles, and that's why this is, there are two periods here. So here, that's why it's called the main peak. So in radio is the main peak. And look what happens. So radio is coherent, it's very different, but maybe related, and we'll come back to this. Let's look, starting from non-thermal X-rays. At above 2 keVs, the profile is main peak dominant, main pulse dominant. Then it switches to the interpulse dominant at the high energy end of the first band. Then we're back to the main peak, main pulse dominant at the low energy part of the second band. And then we're back to the interpulse dominance at the high energy end of the second band. So this evolution is repeated in the two spectral bands. And that's another indication that inverse Compton may be at play, because in inverse Compton, presumably these are the seed photons and these are the inverse Compton photons. So they know about each other. That's another argument in favor of inverse Compton. Okay, with Dill it's not so obvious, but you can trace every gamma ray peak to some non-thermal peak mirror image at the low energies. Okay, now then there is a need to construct an inverse Compton model. And unfortunately, off-the-shelf so-called synchrotron self-competent models are not applicable. So in AGN community, in equivalent nucleus and in gamma reverse also, there is this. There are a few codes that are called synchrotron self-competent. But usually they assume a random magnetic field of a given value, isotropic particle distribution, and sometimes, and especially in AGNs, there is a single Lorentz factor that is shooting at you. While here we have regular magnetic field within the magnetosphere. It is changing sharply within the emission region as R cubed, 1 over R cubed. There is strong radiative losses, so you expect highly non-isotropic particle distribution. And also, most importantly, there is a continuous V parallel, there is a broad distribution in parallel velocities. So, and then I did my own model. It's a simple 1D model, and what I assume is that there are two counter-streaming components. And the presence of two counter-streaming components has been the assumption within the outer gap models from Chen and Ruderman 86. That for 20 years there has been also discussion where is the emission from the back inward going beam. So this is not something I invented. This has been in place already. So I have two components. The one that is going out produces cyclotron, Doppler boosted cyclotron, which is seen as X-ray emission. The one that is going in also produces cyclotron, but the one that is going out is kicking this and gives me inverse Compton. Yes?
Why does the outgoing beam produce cyclotron?
Oh, we'll get to that. Initially, it was just an assumption.
Because obviously, as you all know, it's going from a region where the synchron cooling is very, very fast.
Excellent question. Initially, it was an assumption, and then I realized that there is a motivation for that assumption. So what Chris is saying, that the outward going beam starts with no gyration. Why is it producing cyclotron motion? So initially, when I was doing the feed, I assumed, but then I realized that I can justify it. Yes, and the scattering quickly goes in what is called Klein-Nishin regime. Klein-Nishin regime is when in the frame of the electron, the photon has energy more than mc squared. So the electron has a strong kick. And the good thing about that is the photon, at least in 1D, simple 1D approximation, the photon then almost gets the energy of the electron. Meaning, by looking at the inverse Compton spectrum of the photons, you measure directly the distribution function, the parallel distribution function. Okay? Here is so I need to switch from Thomson regime to Klein-Nishin regime where you develop the delta function. So, a bit quickly, details. Roughly speaking, there are 4 observables and 4 unknowns. The 4 observables are typical energies of the cyclotron peak and the inverse Compton peak, and the typical fluxes of the synchrotron and the inverse Compton components. And then there are 4 parameters, which is the typical emission location that controls the magnetic field, the typical Lorentz factor, the gyrational velocity, and the multiplicity, how dense is my plasma. So 4 and 4, that's good. And I can place it, the emission radius typically 15-20, Lorentz factor 2000, not like 10 million in the inverse, in the curvature, it's a few thousand, that's what everybody expects. Multiplicity is a bit, the plasma is somewhat dense. 10 to the 5, 10 to the 6 is a bit denser than is expected, but we'll get back to this. And there is a non-zero gyrational motion, non-relativistic. So it's a cyclotron, not a synchrotron. So what I stress here is there is, at the first step, there is 4 parameters and 4 knowns. So it's not over, there are not too many free parameters that I'm playing with. I can do better if I want to fit the spectrum. And here is the spectrum fit. There is now more parameters. Now the inverse Compton component basically gives me constraints on the distribution function. And then it kind of maps into the synchrotron component. And there's a couple of free parameters that I played with. One was the gyrational motion. And, but I'd like to stress that this is a data feed. It gets 10 orders of magnitude in energy, 4 orders of magnitude in flux. There are free parameters here, but there are, most of them are measured from the demand to fit the distribution function. You know, if I want to fit it better, I can probably introduce more parameters. But you know. Yeah. Okay. So here is my, then I can measure the distribution function. Here is my distribution function, which again ranges in a very broad range, and it peaks at a few thousand, the Lorentz factor is a few thousand. And different part, there are 3 breaks and exponential cutoffs. But this is kind of all needed to reproduce this bump. Okay? Now, so the important part is a typical Lorentz factor is only a few thousand, and that is what very reasonable. Well, curvature models require 10 to the 7. The one thing that is different from expectation is the multiplicity, which is how more dense than the minimal density. The multiplicity that I use is 10 to the 6 to the 7, which is on one hand high. But it is, I think, still reasonable, because we know that from the observation of the pulsar wind nebula, we know that the average multiplicity is 10 to the 6. To explain the emission of the Crab nebula, the pulsar should produce average multiplicity of 10 to the 6. I can easily see that occasionally I get 10 to the 7 due to some variation. So this is highish, but I still, this thing is still reasonable. What I also need is I need this gyrational velocity to scale as radius to the cube. And initially this came out of the blue because that's what feed the data. But actually there is a motivation for that. We'll get that again. Importance of the pair production in the gaps. You know, if Compton scattering in Klein machine is important, then the pair production is important. So that adds additional complications.
Where's your gap?
I don't know yet. This
It's
model
all happening close in.
Now this happens
You said 14.
from 20 stellar radii up to the light cylinder.
Oh,
Yeah.
but what X-rays would be produced at?
From 20 up to light cylinder.
And the need to have it, but why would it naturally come out to be continuous? a broadly distributed radius, because the synchrotron cooling times or cyclotron cooling times are a very strong function of radius.
Yes, there is, so the idea for this work is there are some very complicated processes that produce my distribution. So let me, from radiation modeling, infer that distribution. As you say correctly, I think you implied to say, or at least I was implying, that there is some extra mechanism that excites gyration. And what I assumed as a simplification is that this gyration goes as the, well, no, it's not that I assume. The fit requires this.
To get the broadness of the synchrotron spectrum.
Well, yeah, something like that. So Pepper, yeah, but generally it's a very complicated problem. And it's a good question, where are the gaps? I don't know. But they're there, they accelerate, then they shut themselves off. And plus, this is probably not highly non-stationary regime, because in the Klein-Machine regime, you don't reach a radiation reaction limit because, because it is likely to be highly non-stationary.
But as you know, with the simplest gap models, it's very hard to get such high multiplicities.
Yes, yes. But this has been generally neglected. Yeah. And yes, there are issues. And that was one of the referees said, oh, I want to see full model of the, full kinetic model of the magnetosphere. Yes, this is the question, but I don't know yet the answer to that. Yes?
Can you explain what you mean by gaps?
The gaps is the regions where there is electric field parallel to the magnetic field. And typically in these environments, the moment you have a little bit of electric field parallel to the magnetic field, a particle is accelerated, then a pair produces through some mechanism, either through curvature emission or through inverse Compton. And now you have pairs that are accelerated themselves. They also produce pairs, so you have an avalanche. So suddenly you have a lot of plasma. And if you have a lot of plasma, you kill off your parallel electric field. So you have a region, a gap, where there is parallel electric field, and then you kill it.
So what does the, sorry to interrupt, what does the heating here? So you need some sort of perpendicular heating to get this gyration.
This is really exciting, that's why I'm going to probably help you guys. And actually, not in this room, but on the 12th floor, 15 years ago, I gave a talk that explains this heating mechanism. So I don't know if Norm remembers it or not. That was my favorite radio emission mechanism for generation coherent radio emission. So here's perhaps one of the most strange things that you ever heard in physics. Let's take straight magnetic field in plasma. Let's shoot a particle along magnetic field with no gyration. Straight magnetic field in plasma, shoot a particle along the field with no gyration. It turns out that under certain conditions, that particle can emit a cyclotron photon. Doesn't make sense. How can it emit a cyclotron photon? It has no gyration. The mechanism is called anomalous cyclotron resonance. And it's a Cherenkov type process. You know that if a particle goes with the velocity larger than the velocity of a wave, it can emit a wave, this wave. With this anomalous cyclotron resonance, if a particle goes faster than a wave, normal wave of the mode, it can emit a wave and undergo transition in gyrational motion. And what it does, it goes up in Landau levels and emits a photon. It's very strange. Usually go down and emit a photon. Here it goes up and emits a photon. Because in its gyration frame, it's emit a negative energy photon. And this process can be unstable. Unstable as a laser type unstable, meaning one particle emits a photon, and then other particles want to emit photons in coherently with this one. And the instability requires a positive gradient. The energy inversion condition, population inversion, now requires more particles on the lower Landau level than on the high Landau level. And that's exactly what you have for this beam going out, because it starts with all the particles on the lower Landau level. Okay? And so the emission is at the anomalous, it's this minus sign. And the main conditions. And then I understood that it does predict the scaling for the transverse, for the gyrational velocity, exactly what I need from the feed. So this is, there are some issues here that need to be worked out. But this feels very sweet. Possibly you can explain all the non-thermal emission from tens of megahertz to hundreds of GeVs, like 18 orders of magnitude within one model. Maybe maybe it won't work, but at least it feels sweet.
To get the right dispersion relation of the modes, do you need some target plasma?
Yes, you need plasma. You need, like with any Cherenkov,
Well,
you need.
outgoing particles are plasma, but
Yeah. Well, like with any Cherenkov, you need waves with refractive index larger than unity, and that is possible only if you have plasma, and that is very in pulsar spheres you do have these modes.
what, practically speaking, what number densities the background plasma do you need relative to the beam?
That was another issue for me, because you need high densities, and at that 15 years ago, as grade school, everybody was telling me, oh, it's 1,000 and no more, and things were not working out well. Now, I measured that millions, and millions would be good, but it still needs to be worked out, the details. Plus the two components, that's very good, because there is no bulk dilution, and that also helps a lot.
So out of curiosity, what makes this sort of a laser type process as opposed to just a random walk? Right, you emit a cyclotron photon and then you absorb a photon and come
You
back.
have a population inversion. Population inversion, like in a laser, means there is more particles that want to emit a photon than those that want to absorb it. And then when once randomly emits, the wave jitters these ones that are sitting there, the wave jitters them, and then they all emit into this mode in coherently in resonance. That's kind of induced emission. Okay, good. So the conclusion that I draw from this is that the inverse Compton emission may be the dominant high energy emission mechanism in the majority of pulsars. And of course, it's not clear, maybe Krabbe and Vila and Geminga are the exceptions. I don't know, more work by the community needs to be done in comparing different pulsars. Before going to a second part of my talk on the nebula, let me take more questions on the Krabbe pulsar.
Well, there is generically another possibility for heating of, for making pairs, and that is that you have some sort of top-down process where you distort the magnetic field and you create a high wave number tail for magnetic spectrum, and then puts all the energy into the particles. And I was able in the paper a few years ago to explain the period cutoff of the magnetars using that type of process. So
Definitely, yes.
high multiplicities are very natural in that
Yes.
type of process.
Very, very good. I have similar feelings and ideas that there are reconnection at Y point, something like that. Yes, yes, definitely, yes. Yeah.
So I'm moving to question. So you say gamma is about 2,000. So this is the gamma of the pair-produced plasma? That's
Yeah, that's, so I have a very simple model. I have two counter streaming beams with and each of them has this distribution, and the typical bulk is 2,000. And sure enough, there is this issue with where is the inward going beam, so it's an oversimplification. But that's kind of, well, the peak is, what is it, a few thousand, few thousand and before.
So is this the cutoff due to the cooling? Synchrotron cooling is cut off?
No, I don't do the detailed radiation model, meaning I don't solve kinetic equation of the cooling and heating, because, say, I didn't know what is the heating mechanism of the transfer gyration. This is kind of the outcome of all these complicated processes, outcome averaged over the whole hemisphere. This is probably highly non-stationary and evolving. This is the average thing.
This is bulk gamma factors.
These are bulk gamma factors, yes.
Presumably accelerated by the parallel electric field.
Presumably parallel electric field creates this.
You know whether that's consistent.
Yeah, but it's not yet a full electromagnetic model. This is just the model of measuring of the outcome of the pair production and acceleration.
I just wonder if this size of is any physical basis behind this. Scam is about size.
He's just fitting a model.
I know.
Sees the observations and fits it so easily.
Yeah.
But presumably the 1,000 you were talking about, that's where the pair production shuts things off anyway.
That's right. That's right. Yeah. Because if it's too high, you generate too many. If the Lorentz factor is too high, you generate too many pairs, and then that tends to cut you down. To cut off the electric field, to cut off your Lorentz factor. And for 30 years, people have been doing this, and the few thousand is what they generally agree upon.
Let me ask you about the multiplicity here. Right? You were saying, so Chris has a possible mechanism for doing this, but this is the multiplicity of the beam or the background plasma? I'm a little confused as to what the multiplicity refers to.
Oh, no. The beam has a gold-right, presumably. There is a primary beam, which has gold-right Julian, and then there is a secondary plasma.
Right.
So that's the multiplicity of this secondary plasma.
So it's just floating around, making N. It doesn't have anything to do with the beam.
I don't know. Maybe it's the beam. Maybe it's, I don't know. Again, it's this question of highly complicated, highly nonlinear problem. Because the more pairs you made, the less electric field, less photon.
So let me just, you didn't mention this, but my recollection is, doesn't most of the energy the spin-down energy come out in these high energies?
No. In best cases, you can get percents. Few percent. Most of the energy still comes out as a wind. The dissipated part is sometimes 0.1%, most of the time. In few exceptional cases, it can be as high as few percent, maybe 10%. But it's not in photons. It's the wind that carries most of the speed.
I think what he's saying is right, yeah. I mean, it is interesting that the efficiency of the gamma goes up as the period increases, right?
That's another thing that I dropped here. But no, yeah. So most of the energy still goes. So this is still a small contribution to the general speed down. In Crab, I think it's 4%. It's very small in Crab, and it's high in some other pulsars.
Now what about the giant pulses?
Well, the giant pulses, they're radio. They have very little energy. They're hugely bright, but they don't have much sugar. Okay, good. So the second part is the Crab Nebula. And this has been a major event, major development in high-energy astrophysics a couple of years ago, which was first seen by Italian Agile satellite, and then next day confirmed by Fermi. So here is a flux of Crab Nebula. So now we're looking at a few days, and each point is averaged over a few days in the case of Agile. And you see that there was this 4-day flare where the average flux jumped by a factor of few. And these kind of flares have been repeatedly seen now for a few years. And they generally have these features. A few days increase in the 100 MeV to GeV flux, about once per year, randomly. Nothing out of energies, nothing related to the pulsar. Pulsar doesn't show anything. And most importantly, the time scales associated with these flares are much smaller than the dynamical time scales of this inner ring, and even smaller than the dynamical time scale of the closest, well, kind of comparable to the closest feature, but still shorter. So they're very, very short compared to the dynamical time scales. And the implication is that these should be kind of localized intermittent events that somehow, suddenly, small event is able to dominate average emission from the whole nebula at these energies. Okay? And that, I think, leads us to the strong reconsideration of the most basic assumptions about how pulsar wind nebula function. And I will explain why. There's a contradiction. And contradiction is the following. On the one hand, the morphology of the pulsar wind nebula is very well reproduced with low magnetized winds. Low magnetized winds meaning the most of the energy is carried by the particles, very little by the magnetic field. So here are 2D simulations of, I think this is Komisarov and Libarsky, and here is a bit. Look, it looks very, very good. You know, they have also, you zoom in, they see some very particular features that are always there in the simulation. So it does look very, very good. So until recently, people, everything is solved. They need low magnetization, the sigma meaning the energy, it's the ratio of the pointing flux to the particle flux. It's very, very small. Okay? On the other hand, here's a spectrum of the Crab nebula. This is synchrotron. This is inverse Compton component, so they have a break at about GeV. The synchrotron breaks at about 100 MeV. Okay? So this is the Fermi data. And the flare appears something like this. It appears in the lowest energy, in the highest energy synchrotron, there is a bump there. Okay? With a break at 400 MeV. Okay? And even before the flare, with the jet break at 100 MeV, I thought it's a bit too much for the following reason, the same reason. Accelerating electric field typically less than magnetic field in astrophysics. So let's equate acceleration by electric field, which is a fraction 8 times of the magnetic, to the radiation, to the synchrotron radiated losses. And then you find that the maximal energy of a synchrotron photon in the rest frame is about 100 MeV. But again, this assumes that electric field equals to the accelerating electric field equals to the magnetic. So it's an absolute limit. But on the other hand, Fermi acceleration mechanism, which is stochastic, this factor is typically much, much smaller than unity. Percent at most, usually hundreds of percent. So this, but even without a flare, we see a break at 100 MeV. So that, in my mind, even before the flare, excludes stochastic shock acceleration. And this is a very strong point, because in astrophysics, though few crazy people did mention reconnection, but it was universal that non-thermal particles are accelerated by shocks. And here is an example where from observations, shocks cannot do this. And so there may be, that's the paradigm change. Some or most, maybe most particles are accelerated by magnetic reconnection and not shocks. And as I mentioned, even before the flare, I was thinking that 100 MeV is a bit too much, and I was kind of constructing a simple high sigma model of pulsar winds where the reconnection plays dominant role. Of course, my simple model is not as detailed as detailed simulations of, but it kind of reproduces qualitatively. Anyway, I will argue that reconnection is an important factor in accelerating particles in pulsar wind nebula. And reconnection is a process where you have counterline magnetic fields that move towards each other, then reconnect and fly out. And there are two generic regions within the pulsar wind sphere, within the pulsar wind nebula, that you can have these counterline fields. First on the equator, and second on the axis. So these are the two possible reconnection sites. Now, as I mentioned, reconnection is a process where magnetic fields flow with plasma. There is a highly resistive region, and then they pull apart. The plasma is pulled apart. Now, in a relativistic plasma, where you have B squared of the order of rho c squared, where the energy density of magnetic field is of the order of the matter energy density, where alpha speed is of the order of unity. This reconnection inflow velocity can be of the order of unity. And since there is magnetic field here and you are bringing it in, there is electric field out of the plane. And eventually, it's this electric field that will be doing the acceleration. And an important part is that in reconnection, if the inflow velocity is relativistic, this electric field can be as high as the magnetic field. And maybe a little bit more, because, well, the electric field here can be as high as magnetic field outside, but inside magnetic field is dissipated by resistivity, so it can be even higher than magnetic field locally. And Uzdiansky was looking at this kind of models, but what he was looking for, kind of stationary Speed-Parker reconnection layer. Everything is stationary. But we know that it's a flare. It's a highly non-stationary event. So what we did two kind of models. The first is mini-jet, meaning suppose that there are these reconnection events that happen randomly within the pulsar nebula, and they shoot some blobs of plasma. And let's do statistical analysis of it. What kind of signal we expect from this? And this comes from models that we did for the gamma ray burst. But anyway, even if the intrinsic process is purely Poisson, meaning you shoot randomly, since during the Doppler boosting, you will be the observer will see mostly, basically only those jets that are shooting at you. So we can calculate the probability of a flux, which goes as 1 over flux, meaning the average flux is dominated by rare bright events where this jet happens to shoot at you. And that's good because the flux evolution of the nebula is definitely non-Poissonian. And then we can get the power spectrum, which also shows power law and dependencies. And that feels good because I start with Gaussian and I get a power law. That's good. I get intermittency. Now, since I'm at the radiation reaction limit, if you start with some pre-injected distribution, after you reach radiation reaction limit, you start piling particles at the radiation reaction limit. So basically, your particle distribution will be monoenergetic, not a power law, which is typically, and that's exactly what we see in the observations. So we can fit this power law with monoenergetic distribution.
So wait a minute. You're explaining these flares in terms of synchrotron.
Yes.
And what's the energy of the particles we produce? You know, the bigger field in the nebula, more or I mean, obviously simplicity small.
No, I don't know why sigma is small. I'm not sure I understand the question.
Well, assuming magnetic energy density is comparable to the total energy density, what's the energy of the particles you need?
Oh, we are at the radiation reaction limit, which Lorentz factors of the order of 10 to the 8, I think, 9. That's huge, yes. But the idea here is, you take a small number of particles. So this is a Doppler factor. So Doppler 1 meaning they are stationary with respect to you, and you see that the normal has no effect on the average spectrum. You take this small blob and you boost it by Doppler factor 3 only, and it becomes highly dominant. Because your spectrum is diving in exponentially. If you can take a small blob and move it a little bit beyond through the Doppler factor, it will be a huge spectral bump. Okay. So what produces these? So this is the statistical description. Now the physical description. And the point that I would like to make is magnetic dissipation. Magnetic systems are very highly nonlinear systems, and meaning you can start with something very smooth, and suddenly you will have highly explosive event. And for example, a few years ago we were studying what is called tearing mode instability in highly magnetized plasma. So let's take a very simple, smooth distribution of magnetic field and currents. Magnetic field just does this, not just current sheet. And then we perturb it, and we see that it breaks in what is called magnetic islands into what's called tearing mode. Now, today, to make this break, at some point, you will need to form what's called the X point, where magnetic field goes like that. And what is interesting, if you squeeze this X point a little bit, the tension here will dominate tension here, and this you will have an explosive development. Explosive meaning you will reach finite time, you will reach singularity in finite time. So in finite time, you form a current sheet. Here is kind of parameter A, which is kind of the disbalance between the two. And it goes infinite within the Alfvén time scale of this whole system. And of course, during these moments, you will have strong inflow velocities of the order of the Alfvén velocities. So, I have explosive dynamics. We start with smooth conditions. Electric field will be of the order of the magnetic field outside, and if we have dissipation, it will be probably larger than the resistivity. And also, all particles that you initially see everywhere, they're all squeezed. So the particles are all squeezed towards this reconnection region where the magnetic field is low. So this model has all the right ingredients: explosive, inflow velocity of the order of the Alfvén velocities, and particles are advected towards the reconnection region, the current sheet from current sheet. So,
do you expect your distribution function to be anisotropic here because the reconnection produces only parallel heating?
Yes, yes.
And then you need to somehow redistribute it.
Not necessarily, It's yeah. If it's this electric field, it can accelerate more, and that may be good. Yeah. So this is you don't necessarily need to scatter. Maybe it's good because it's anisotropic and it's streaming at you, and that's the beam. That helps. So conclusion. So I tried to argue that this recent observational result, all of this has been discussed before. But there are these observational results that lend strong support to the two ideas that inverse Compton may be the dominant high energy emission mechanism in the majority of pulsars, and reconnection is an important, perhaps dominant mechanism of particle acceleration in pulsar nebula. And many models of active galactic nuclei and gamma ray bursts build on the experience that we get from pulsar nebula, so by inference, reconnection might be important there as well. Thank you.
Is there any additional question?
A lot of this is being based on the time scale, right?
And maximal energy. There is the, well, everything, at least to me, everything started with this. It's too much. Even the stationary break at 100 MeV is too much for synchrotron. And then you're trying to find ways out of this problem.
So, do you have to find some other explanation for the match between the pairings of the nebula and the nebula sigma?
Yes. Yes. And what Komisarov is doing now, he has a wind which is strongly magnetized near the axis. Well, it's zero magnetization on the axis. Then it becomes highly magnetized at the intermediate and low magnetized in again. And with this, he can reproduce some morphological features, but he loses others. But generically, that is, I think, a correct way of going, because there you can retrieve both morphology and localized regions, localized magnetically dominated regions. Then there is a question, there is a shock in the particle dominated, then there is a reconnection in the magnetically dominated. What's the interplay between them? These are all open questions, but yeah, that's the way to go. Probably. Maybe you can do it all through magnetic reconnection, but
Yes. Two questions about the first part of your talk. You observed the spectrum shows two bumps. Observationally, the second bump is narrower than the first bump. Does it contradict with the...
it's not narrow, it's logarithmic.
Yeah, no. In the
So
log space, it's still narrow.
No, it should contradict.
Because the inverse content spectrum should be more spread out than the CITA spectrum.
I don't know, it's about 4 orders of magnitude here, about 4 orders of magnitude. I don't know. This comes out of the code. So.
Okay. So the second question, do you expect a second order inverse component?
Barely. At a multiplicity of 1,000,000, one particle produces of the order of 1 photon. So if multiplicity is higher than 1,000,000, then few particles produce a photon. And that also goes back to the radiation modeling, because in Klein-Machine, it's 1 photon is a big back reaction. So that also affects the bump motions.
Okay, there are no additional questions. We can continue the discussion upstairs with some cookies. Let's thank the speaker again.